The start questions have been posted, so if you've got any questions on those, we can talk about those as well. All right, so, and apologies, I'm still a bit clogged up. I don't think I'm infectious anymore. I heard a terrible story yesterday when I accused one of my fourth-year students of infecting me. He said, no, he'd had the cold last week, but he was better now, which is great. But he told me that, you know, people, when they have a cold, they come to lectures anyway. They don't feel any responsibility to stay at home. They figure they've caught the cold from somebody else, and now it's their turn to share the love around. Is that right? Is that what you guys do? I suspect 9 out of 10 people are not being truthful here. That's terrible. All right, I thought COVID had taught us that we should be a bit more respectful of other people and stay away when we feel bad. All right, or when we're infectious, even if we don't feel bad. Okay, so we're going to start talking about algorithmic state machines as a model, a means of describing digital systems. We're going to look at 2 examples of their use today, and then we're going to go over I think 3 or 4 more cases next week. But I want to get through these today so that you've got some insights, and those that want to forge ahead with the labs have got the background to be able to do so. So algorithmic state machines are a special type of flowchart. Now, you guys probably don't know what flowcharts are either, or probably haven't used them if you even know what they are. But essentially they're a graphical device for describing computation. Flowcharts are anyway in general. But algorithmic state machines are a special type of flowchart. They're restricted to just 3 types of symbols, whereas flowcharts, I think there were probably 30 or 40 different types of symbols that were developed over time and used at various levels of abstraction in systems to describe those systems. Importantly, what we use in ASMs are firstly a named state box. So this is a rectangular box with a state name and a colon that defines the name of the state. And inside this box, it might be empty, but if it's got things inside there, then these are actions or signals that, more like outputs, are always going to be asserted in that state. All right? So these are sort of always on while we're in this state. The state, may have several, it might be a large state, it might have many different actions, many different decisions and conditional outputs as well. But these guys that are listed inside these square boxes are always on for that while we're in that state. The second type of box, which is very common in flowcharts as well, is to have this sort of diagonal, diamond-shaped, conditional or branching expression. So we have some conditional expression that is evaluated, and if it's false, we take one branch, and if it's true, we take the other branch, and we label the corresponding branches 0 and 1 to indicate which is the false and which is the true branch. And thirdly, we have these so-called conditional output boxes. So these are usually dependent upon some conditional expression being true. And they're listed in these sort of oval-shaped boxes, elongated ovals. So these are outputs that are only valid or only going to be asserted if a particular condition that led to this this branch is found to be true. Okay, so these correspond roughly to Mealy-like outputs, and we'll see how that works in a couple of examples before looking at it in practice with real systems. So just to show you how you can use an ASM chart to implement or to describe or similarly replicate the functionality of a state diagram, recall that we had this more type state diagram for our first finite state machine that was a sequence recognizer that recognized instances of 2 or more ones in a row. Do you have a question? Or? Okay. So we had this state diagram, recall. So to describe the same finite state machine using an ASM, it could be drawn like this. So for every state that we have in the state diagram, there's a labeled state box here, and only one of them asserts the Z output to be 1, so we just list Z in the C state, okay, because it's not active in the A or B state. Note, however, that the direction or the transition that's taken is directed by what the input is. So if we're in state A and W is 0, then we remain in state A. But if W is 1 on the next rising clock edge, then we would enter state B, all right? Similarly, in state B, if W is 0, well, we return to state A, but in state B, if W is 1, we enter state C on the next active clock edge, and the same is true here for the ASM. If W is 0, we return back to state A, but if W is 1, we enter state C. Okay, and we stay in state C while W is 1, but when it becomes 0, we return to state A. Okay? Are there any questions about the one-to-one mapping here between the two? Okay. Other than we don't explicitly say Z equals 1. It's implied that if it's listed that means it's active. And in this case, Z is 1 is active.
What happens when we go back from C to A? How does it know to change Z back to 0?
Well, C is simple. So this is only active in that state. So any of those outputs is only active for that state. So you'd have to list it again if you wanted it to be active in state A as well. So by virtue of the fact that it's not there, yeah, it's not, that means it's cancelled. Any other questions? Okay. So the Mealy machine for the same problem we also looked at previously. Remember, it only had 2 states. So if you got 2 or more ones in a row, you would have the one being output when that second one came along, and for every subsequent one, there'd be a one being output. So the corresponding ASM chart is depicted here, whereby if we're in state B and W is 1, then we would output Z. Output Z is 1. And return back to state B, just as is indicated here in the state diagram. Any questions on this one? Yeah?
When we return back to state B, are we not supposed to make it go directly to the B column? Because it's going to the arrow that's going to B. Do we always do that?
Yeah. By convention, this it wouldn't really matter. As long as it's clear what the intent is, it wouldn't really matter. Yes, here the arrows converge to indicate that they're both going to B, but it wouldn't matter if you had the arrow going straight from Z into the side of B. It'd be the same meaning. Any other questions? Okay. All right, so let's have a look at this, how it plays out in the real world, and we'll look at this in the context of a design problem. And the design problem is to devise a pop count circuit. So the problem is to devise a circuit that will count the number of bits in a word that are on. That's known as pop count, the pop count operation. So what I mean by that is, here's pseudocode for that operation. And if you wanted to code it in a your favorite sequential programming language, you'd probably write something like this, whereby you're counting or masking off the ones that are in the word and counting all of those instances where it's actually one. In our case, we're going to clear the counter, and while the word that we're checking, well, that we're trying to determine how many ones are in it, is not yet 0, if the least significant bit is 1, then we increment our counter B. Otherwise, we shift that word A to the right. So eventually, we're going to shift all of the bits out to the right, and we're only going to be left with zeros, assuming we're zero filling from the left, assuming it's a logical shift right, not an arithmetic shift right. Okay? Does that make sense? Now, what we're trying to do always is design a circuit that implements that algorithm. Okay? So that we're not going to be programming a processor as such. We want to hard code the hardware that we need in order to perform this circuit, and obviously the control of that hardware. So that raises a number of questions. The first might be, what data path components do we need to perform this operation? So it seems from the pseudocode that we're going to need a counter, we're going to need a shift register that's going to store this initial word and shift the bits out one by one, right? Is there anything else that we need? Well, we'll need some logic to figure out whether A is 0 or not. Sorry? Well, yeah, we're going to be comparing with 0. So what's a way that you can determine whether all of the bits of a word are 0 or not? Yeah, very good. A NOR gate will do it. So if you just OR all of the bits together, you'll be instantly able to tell whether there is at least one 1 there. So the way to determine that there is no 1 there is to NOR it, right? To negate that OR output. Okay. Secondly, you know, when you have these various components, how do you control them? How do you coordinate them? How do you orchestrate the algorithm? And it's not at all clear, you know, we haven't really discussed it so far, how you might transfer the input and the output for this circuit. So that's something that you need to consider in general as well. Okay. So, here it is. Here is an ASM chart that performs this operation. Now, this might be a little disorienting at first. There are different colors here, and doesn't seem to be initially an immediate coordination with that pseudocode. Well, let me tell you or explain that the blue bits effectively encode this algorithm. The gold bits that you see here are part of what's known as the handshaking hardware that you need and the handshaking operations that you need to perform in order to be able to use this circuit. Somehow, the user of the circuit has to be able to inform the circuit, I've loaded that word A, and you can start checking how many bits are on. And somehow the circuit has to inform the user again, the user circuit, the environment within which it resides, I'm done with counting how many bits are on, here's the result, right? And so that's what this gold stuff around here does. In effect, we allow the user, the user will be loading the word A, right? They're the ones that are providing A, so let them load that word into whatever shift register we're going to be placing A into. And when they're done, they're going to assert a start signal S, because only then does it make sense for the circuit to check how many bits are on? You know, if there's no word to be checked, then the circuit, there's no point in operating the circuit. So the circuit then goes ahead and does this operation that's described up here, namely checking whether A is 0 already, checking the least significant bit, and if it is a 1, then incrementing B and shifting the word to the right again, okay? At some stage, if we keep shifting this word to the right and filling it with zeros, that word's going to be 0 all up. No bits are going to be 1 anymore. And when that's happened, we know that we've counted all of the ones that are there. Therefore, we can indicate to the user that we're done, and therefore output some sort of flag to say, we're done. You can now read the contents of B, which contain the number of bits that are on in your word A. And the circuit will stay in this state until the user has read that word B and indicated that they've done so by deasserting the start signal. Deasserting the start signal indicates to the circuit then the user's finished, we can return back to the reset, the initial state. Okay? So this start signal is a really important handshake signal that's used to coordinate the activity of the circuit. And the done signal, of course, also plays this role of flagging when the circuit's done. So the orange bit is really part of the handshaking, and we won't necessarily explicitly encode much of that, because basically we'll assume that the user provides us with that word, and we just start whenever they indicate that we're ready to start. So there has to be some sort of trigger to start the circuit, and there has to be some sort of flag to indicate that the circuit's finished whatever it has to do. It's really worth mentioning now, I think it's more clear from this ASM chart than it is with the previous two examples that we looked at, where we just looked at FSMs, that the ASM chart integrates data path activity, like incrementing B, checking whether A is 0, shifting A to the right, together with the control that we've seen in the finite state machine, namely, not going into this second state which basically covers the loop here of the pseudocode until a start signal is obtained, and not exiting and flagging that we're done until we're finished with all of the bits that are on in that word A. So we're integrating data path and data flow activity together with control in the one chart. So they're a bit more useful than just a finite, or just a state diagram, if you like, which was really only used for capturing control. Right, now this last point's really important. Okay, if you look at this pseudocode that we have up the top here, there's really only two states here. There's an initial state where we clear our counter B, and there's a second state where we're checking the contents of the word A and shifting the bits over and incrementing for every bit that we... So although it's quite a lot of activity that's done there, that's really only the second state that the circuit's in, right? It's either in the initial state or it's in this computing state. And it does actually enter a third state down here, as we've discussed, where it's finished and it's waiting for the user to simply indicate all done, all good, you can reset yourself. Now, this point here is really subtle, and it might take a while to get a hang of, much like a few things have taken a while to get a hang of in digital circuits and systems. This shift right A that's listed as a more type action inside this state 2 doesn't get done till the end of the while loop here, right? But here it's being listed right up front. And that seems a bit weird. What, we shift right first? That means we're always going to drop that very first bit, that rightmost bit. But if you think about it, no, it doesn't. All this is saying is, in this state, we're always going to be shifting right, i.e. we're going to assert whatever signal it is that tells the shifter to shift to the right. But of course, that action won't take place until we get an active clock edge, right? You can't do a shift until the clock edge loads flip-flops, right, across the register. So that action, while it's asserted as soon as we come into this state, it hasn't yet seen an active clock edge to actually be done. Now, it may very well be that the word A is 0 to start with, in which case we'll take this path, and the very first active clock edge that comes along is going to take us into state 3. That will shift A to the right, so it'll shift 0 and make it 0, but it'll also raise done, etc., and we'll have done none of this internal stuff in state 2. On the other hand, there is, A is non-zero, in which case we'll take this branch and we'll check whether the least significant bit of A is 0 or 1. And it may be that the least significant bit is 1, in which case, again, we're going to assert the action to increment B. But that won't actually take place until the next active clock edge takes us right back into state 2. It's the active clock edges that cause these actions to be performed. Other than that, this is just a signal. All I've done is enabled a shift register. All I've done is enabled a counter to increment. All right? And I'm waiting for a clock edge for that to occur. And I hope that's clear. It only occurs when I enter a state again based on, or enter one of these state boxes based on the occurrence of some active clock edge. Are there any questions about that? Yeah.
If the number is just 0, 0, 0, 0, 0, 1,
Yes?
then wouldn't it just drop the 1 and go to done?
I just told you it won't. So what happens is we've got 0, 0, 0, 1, right? You come into state 2. It enables the shift register to shift to the right, but it won't have done that yet. Because prior to this state, in state 1, there's no signal telling the shifter to shift to the right. So that only gets asserted after an active clock edge takes us into state 2. When we're in state 2, that signal gets asserted. So the first time around, we will see A is not 0. We'll see the least significant bit is 1. We'll go to set the increment to take place. The clock edge comes along. We increment B. We shift A to the right. And now A is 0. And we go out. And B is already 1. Any other questions? I'll show you through simulation how it works. That should confirm it a little bit more. Any other questions before we move on? All right. We're going to have a look at the detail. Obviously, we've talked a little bit about already what sort of data path items, elements we need. We need a shifter, an n-bit register that we can shift to the right. When load A is asserted, it puts data into the register on an active clock edge, and when EA is asserted on an active clock edge, it gets shifted to the right, okay? The word A is the output of this shift register, the least significant bit is A, 0, and we can also check at any time whether or not that word is 0 yet. Z will be asserted when all the bits of A are 0, okay? We've also got this counter over here that initially has to be cleared. So when it gets loaded, we load 0 into this log n bit counter. And when EB is asserted, the counter increments on an active clock edge. So everything takes place on active clock edges. They're synchronous circuits. Any questions about that? Take note of this. In the final exam, I'll be marking you on whether or not you're accurately doing this. Every time you have a multi-bit signal, tell me how wide it is. If it's only a single bit, that's fine. This one's log n bits wide. Only needs to be log n bits wide because there's only n bits there, so it can only count up to n at most, right? Okay, so once we have determined what our data path elements are, then we can refine the finite state machine that we had. Previously, so here, we said we're going to clear B in state 1. We're going to shift A to the right, check whether A is 0, look at the least significant bit, increment B, etc. So by refining the ASM chart, what I mean is back, go and modify the ASM chart, the labels that are used within the ASM chart, to reflect what actually is needed as far as the data path is concerned. We have a shifter that needs to be loaded and enabled, and we have a counter that needs to be loaded and enabled. So when we say clear B, the counter, that means just assert LB. By asserting LB, when an active clock edge comes along, 0 will be loaded into that counter. Remember that the user is going to assert LA, so we don't need to worry about LA. We're assuming the user is going to load that. So that was over here as a conditional action, but we're not going to worry about it. It's going to be in the entity, the interface, so that the user just asserts LA when data is available and waits a clock cycle before asserting the start signal. Now in our state 2, which had as its first action up here shift right A, well, to shift A to the right, all we have to do is assert the enable signal there. So we assert EA there. LB not being asserted means LB isn't being asserted in this state, okay? So EA being asserted means that the next time I enter a state block, be it S2 or S3, that action's going to take place. It's going to shift that shifter across. Z tells me whether all of A is 0 or not. While it isn't, we check that least significant bit of A 0. And if it is 1, then we're going to assert EB, the enable on the counter. So that both the EB and EA being asserted, if I re-enter S2 on an active clock edge, it's going to increment the counter and shift the word A over to the right by 1 bit. Okay? At some stage Z is going to be 1, and at that point, instead of re-entering state 2, we're going to enter state 3. But at that point in time, EA will be active. So we will do one more shift when we enter this S3, but shifting 0 has no effect, so it doesn't really matter. And we're going to stay here asserting the done flag until the user deasserts the start flag, and then we can come back to our state 1. All right? Are there any questions on how the refined ASM chart is obtained from the original ASM chart, this one here, and our determination of what data path elements are needed to perform the computation? Okay, all right, then what we're going to do next is just code that up and have a look at how it operates when it's simulated. I don't think there's too much that's mysterious here, but let's just go over the entity because we've talked about LA being controlled by the user. So this bit count circuit or pop count has got clock and reset in the interface. It has LA, which is one of the internal signals, remember, on our shifter. Data, which is the word that's going to be loaded into our register A. It has, and they're inputs, right? And it has B, which is the output of the counter, as in mode buffer, so we can read that at any time, but it can be modified by the circuit. And done is an output flag, as we would have expected given the ASM chart, right? To code up, to code the design, we basically have to describe the data path and we have to describe the control of it. So this will imply we need a finite state machine. There are only 3 states here. They were labeled S1, S2, and S3. And so that's the state type that I have here. It's just 3 states in an enumerated type. Here's my signal A, which is the output of this shifter. And all of the internal signals, Z, EA, LB, EB, that we've talked about already. Low is just going to be used to implement the 0 that gets shifted into the shift right shifter over here. So there's nothing really too dramatic there. So this first block implements the finite state machine, the transitions in the finite state machine. So the state that we have is called Y, the signal. So it's a synchronous process with an asynchronous reset. So when we have a reset, we want to reset the machine into state S1. That was also captured up here because there was an arrow coming in to state 1 labeled reset. Otherwise, on an active clock edge, depending upon what the current state is, if we're in state 1 and S is 0, which means that the handshake hasn't been given yet, then we want to stay in state 1, which is just coding that edge up. Otherwise, if S is not 0, then we want to enter state 2, which is this edge here that takes us into state 2. If we're in state 2 and Z is 0, then we want to stay in state 2, otherwise we're going to enter state 3. And if we're in state 3, we're going to stay in state 3 while S is still 1, because we're going to wait for the user to deassert S. After done's been raised, we've told the user B is ready, and it's up to them to deassert S. All right, that's that S signal that is in our interface. Okay, any questions about the finite state machine? It's pretty straightforward, it's just the transitions there. But we still need to code all of the outputs. So that comes in the next block up here, this blue guy up here. Now this is a combinational process. It takes the current state and A0 as inputs, or in the sensitivity list, right? So we're talking about coding up what are all of the outputs of our ASM. Since it's combinational, there's no clock there. Since it's combinational, we want to ensure we don't infer any memory, and the best way to ensure that we don't infer memory is to assign a default value to all of the outputs of this process. So in this process, we're going to output these different values, EA, LB, EB, and done. So we're going to assign them a value initially, and based on what state we're in, we're going to override that value, okay? So if we're in state 1, then we're going to set LB to 1, which is effectively just what we've said here. If we're in state 2, we're going to assert EA, and if A0 is 1, then EB is set to 1. So here's the Mealy output. Otherwise, if we're in state 3, we're going to assert done. It's pretty much a straight... So if you do a good design, coding this up is trivial. It's just translating the design back into code. Finally, for the data path, which for many will be probably the trickiest, because if you have the least experience at actually designing data paths, as it were, which is here, well, we have to describe the counter, and we're going to instantiate the shift register that got instantiated. It was one of the components that's in our block of work subcomponents. So it gets instantiated down here, but let's just look at the counter first. It's also synchronous with an asynchronous reset. If there's a reset, set it to 0. Otherwise, on an active clock edge, if load is 1, then set B to 0. That's effectively what this is doing, loading 0 in when it's being loaded. Otherwise, if EB is asserted, then increment the counter B, right? Finally, for the shift register, we've got data that the user provides, LA that the user provides, EA that this circuit provides. Low is just 0. I think it was declared here, defined there. We've got the clock input and A, the word that's currently stored in our shift register. So it's just instantiating that shift register with a size of 8. And finally, the Z output here is set to 1 when A is 8 zeros in a row. Otherwise, it's 0. Okay? That's the whole design. So this circuit will, based on a user providing a word of data, an 8-bit word of data and a start signal, will go away and figure out how many ones are there and report back via the contents of this counter how many ones there are. Are there any questions so far? Okay, then let's do a quick simulation. So this is the simulation that the text provided. Here are the stimuli up the top, all of the inputs, reset, LA, data, the start signal, and the clock. And the responses listed down the bottom here, the done signal, the count value B, the current contents of A, and what state we're in. Okay? So, initially the system is reset. So after the reset, the user puts data of 3B and asserts LA, and when the next active clock edge comes along, we see 3B being loaded into register A. Okay, so 3B is just 0011, 1011, right? So that's, let there be no doubt about where the ones are in this word. After the user asserts S then, on the next rising clock edge, we see the circuit going into state 2. Okay? Now, on that first period where we're in state 2, we see that the least significant bit is a 1, right? So that means we're going to increment B on the next active clock edge, right? And we're also going to shift this guy over to the right by 1 on the next active clock edge. So this is 3B becomes 1, what is that? D, I think it is, over here, right? So here's the active clock edge that brought us into state 2, but it's the next active clock edge when the first actions, the first more action and the mealy action take place, right? So we see B incrementing and A being shifted across by 1 bit. So A currently has these contents then. The least significant bit is still a 1, which means on the next clock cycle we'd expect another incrementation, which we do see up here, to 2, and we see 1D being shifted across to become 0E, right? Yep, 0E. Hang on. 3B, 1D, 0E, yeah, 0E, right. Now the least significant bit is a 0, so in the next clock cycle nothing happens other than we're going to shift A across by 1 bit. It's a more action, so it always takes place. So 0E becomes 7. Now we have 3 remaining cycles where we're going to increment B, 3, 4, 5, and shift across our word A. So 7 becomes 3, which becomes 1, and eventually 0. So on this last cycle here, A is 0, right? A is 0. But it's not until the next active clock edge comes along that we can move into state 3, because that isn't detected until that round where it is 0, right? And so we move into state 3, and moving into state 3 means that the done flag gets raised, and then it's up to the user to deassert S after they've read B, and after S is deasserted on the next rising clock edge, we return to state 1 as expected. All good? Great. Yeah?
I'm still not sure how the counter is able to count. Okay, so when we see a 1, okay, B or load B goes to 1, or enable B goes to 1, right?
When the least significant bit of A is a 1, B is incremented.
Yeah, I'm still not sure how that happens. Like, how does it?
So it doesn't happen instantly. It happens when the clock edge comes along, right? There's effectively a whole clock period where that least significant bit is being checked,
Okay.
and where the decision to increment B is finalized. So that is down here. So we're in state 2. We've just had an active clock edge. We've got a 1 now in our least significant bit. So that means A0 has become 1, which means I also enable B to be incremented. And we wait until the clock edge comes along, and then we go back into state 2 again. And both of those things then happen. A is shifted and B is incremented.
Or if it's 0, it just stops the counter. If A0.
Yeah. So A0 determines whether the counter is incremented or not, and yeah, when the word A is 0, we exit. Is that better? Right. Any other questions? All right. I have one more example. It's somewhat more complicated, but let's just see how we go with it. The remaining designs that I'm going to talk about are going to assume there's a standard package called components that has each of these components in it. I only provide the entities here, not the detail of how they're implemented. I think you can figure out how they're all implemented, but they're detailed in other slides that we've already covered anyway. So apart from a 2-to-1 mux, there's a mux DFF. Remember that has a cell signal that determines whether D0 or D1 is latched into the flip-flop. There's an n-bit register with an enable, which means that when the enable is asserted, the word, in this case R, is stored in the register as output Q. Okay. There's an n-bit right to left shift register, so this guy's shifting n-bit right to left shift register, so from the least significant bit end to the right most significant bit end. So this is equivalent to every time it's shifted, you're multiplying the word by 2. So it has a load signal to be able to start off at a particular value called R, and it has an enable signal that asserts the shifting, and W is the bit that you're backfilling in from the least significant end. Normally that'll be a 0. And Q is the current state of that shift register. Similarly, there's a shift right register, which is the same as dividing by 2 every time you shift to the right by 1 bit position, which also allows us to load a word R or enable it for shifting, and the current state being Q. There's an up counter that counts up to a particular modulus. modulus minus 1 or it has a particular modulus, so it counts up from 0 to modulus minus 1. We can preload it with a particular value using the L signal or just enable it for counting up. And there's also a down counter. It doesn't really matter that whether you remember these or not, it's just that they're provided there as circuits, and when I instantiate them, I'll explain again what they're doing. The second exercise, or the second design that I wanted to look at, was binary multiplication. So it's a little bit more of an important application because we often want to multiply two numbers together. The method that's explained here is just the schoolbook method, and it's quite commonly used. It's not the most efficient, not the fastest, but it's pretty okay. It works. Right, so we know how to do decimal multiplication, I hope. Binary multiplication is exactly the same. So we have our multiplicand, which is the word A at the top here, and our multiplier, which is the word at the bottom. For every one in the multiplier, we add a shifted copy of multiplicand A into our product P. So when the multiplier is 1, 0, 1, 1, the shifted versions become 1, 1, 0, 1, 0, 0, 0, 0, 1, 1, 0, 1. They're all lined up there, and we've got to add all of the bits together effectively to produce that product P. Okay? So it's doing the same thing that we would do in decimal, albeit it's a little less efficient because it's binary. All right, so we want to produce a circuit that will do this. Raises the questions. How are we going to do this computation? What algorithm are we going to use? And once we've decided on the algorithm, what data path components do we need and how are we going to control those? So it's the same questions we looked at for the pop count question, and we'll be asking ourselves these questions at every time we look at a new design. So the algorithm we're going to use is this one here. It's just the schoolbook method for multiplication, which means initially clearing the product, and then for every bit in our multiplier B, if looking at it from the least significant bit end on, if that bit's 1, we add a copy of A to our product. And then we shift A to the left by 1 bit position. So we're multiplying A by 2 every time we go along, right? So that we have the correspondingly right value that we're adding into our product P. That pseudocode all clear? Okay, so an ASM that'll do it is very similar to the previous example. In many ways, it's also a 3-state ASM, has a very similar structure. Our handshake is going to expect that the user loads the multiplicand and the multiplier, and when the user has done so, is going to assert this start signal S. While we're in that initial state, the product P is going to be cleared. After the handshake signal is asserted, we'll move into the big for loop that we have here. In fact, the for loop is turned into a while loop here, actually. It's more like the first one, where we check whether there's any remaining bits in B that are non-zero. So we short circuit the for loop here and exit if there are no more ones left in B. If the least significant bit of B is 1, then we add a copy of A to P. Otherwise, we return back into this state, and in this state, we shift A to the left, i.e. multiply it by 2, and we shift B to the right, i.e. get rid of the least significant bit. Right? And we do that until there's no more bits of B available, and when that is true, then we can say we're done and wait for the user to collect the result and deassert the start signal S. All good? All right, so I should have asked at this point, so what do you think we might need from the data path. What sort of components do we need to perform this algorithm, to implement this algorithm? Yeah.
Left shifter and a right shifter.
How big? How big's your left shifter?
Double the size of.
Correct, 2n bits, right? Because we're going to shift it all the way. We're always adding it to P, and we know that P is going to have to be a register that stores 2n bits. We're multiplying two n-bit numbers together, right? So yes, our left shifter has to be 2n bits wide. The right shifter, how big is that going to be? Yeah, n. It's only storing the multiplier, right? So it's n bits right, wide. All right. What else do we need to be able to do? Check whether b is 0. Same as we did before. Just gnaw all the bits of b together, right? That'll do that bit. How do we load p with 0? So we have an n-bit register which we can create as 2n bits wide, but it can only be loaded with 0, or it can be loaded with something non-zero. It can't be reset to 0. So we have to have some way of storing 0 and p. And loading A, the shift register that's 2n bits wide, is also a little bit tricky, because we want to load the least significant bits with A, the multiplier, the multiplicand, and the most significant bits of A with 0, right? So we've just got to make sure that we're doing that. So that's all described here. Here's our shift register A for A, with n zeros and data A coming in when we load A. Well, the user's going to load A. And our shift right register, which has got the word B in it, that's just going to be loaded by the user. Internally, we'll control the enable signals on these two guys. Now we need a 2n-bit register for the product, P, down the bottom here, and that's going to be adding, well, the current version of the product is going to add another copy of A to it on certain cycles, namely those cycles where the least significant bit of B is non-zero. In order to store 2n zeros in this register, we've got a battery there of 2n 2-to-1 muxes, where each mux has a 0 as one input and a bit of sum as the other input that it's going to write into this register when we assert that EP signal, the enable signal, to load this register. All right. This was our ASM chart that we had. So the next step is to refine the ASM chart based on our data path. So what substitutions do we need to write over here in our ASM chart? Remembering we're not going to actually have this conditional load A and load B. That the user is going to do that for us. So in state 1, we want to clear P. How would we clear P? What signals do we have to assert in order to clear P?
AP equals 1 piece.
Right. I heard EP, yes, and I heard P cell, but I don't want to set P cell to 1, do I? No. I want to set P cell to 0. Right, okay. What about in state 2? What do I need to do there? Enable for what?
The shift register.
So which enable?
Both.
EA and EB both need to be asserted, correct. Anything else need to be done here? In this state, we're always summing the P register and A, right? Always. We're not always writing the result back. But we're no longer interested in clearing, so we can set P cell to 1 here as well. So we're going to do that here. Okay? B0 is clear. What do we need to assert when P is assigned P plus A? Just one signal. Yeah, EP. Okay, good. So we end up with this guy over here on the right, given all of that discussion. It's going to run quickly through the design. Let's not worry too much about the signals. The FSM transitions are exactly the same as for the last one, right? Exactly the same. Same code. The FSM outputs, again, it's combinational Y and B0 this time, so I clear all of the other signals that are going to be set depending upon what state I'm in. In state 1, set EP, right? In state 2, set EA, EB, and P cell equal 1, and if B0 is asserted, then EP is set, right? So that's the mealy output, and in state 3, done. As for the data path, it's a little bit more complicated, but not a lot more complicated than what we saw before. We define 0 to just be a single 0, and n zeros to be a string of n zeros, all set to 0. Therefore, A in, which is the input to our A register, is just going to be the concatenation of n zeros and data A. And here's the instantiation of that shift left register that's of double n bits wide, with A in as the input. LA is going to load it, EA is going to shift it when it needs to, and we're going to fill in with a 0 from the right when we're shifting. The shift register to the right for the word B is just going to have data B as input, loaded by the user when the user asserts LB. EB is the signal that we control when we're in state 2 and we're shifting this guy over to the right. And of course, we're not going to shift either of these guys until the next active clock edge after S2 is entered for the first time, right? Our sum is just A plus P. Here are the 2 to the n, or 2n, 2 to 1 muxes, which have 0 on the 0 input and some I on the 1 input, with P cell controlling them and producing the ith bit of data P, which is the input here to our 2n bit register, the product register down the bottom here, which is loaded when EP is set. All right? Here's a quick simulation of that guy. Reset. We have the user inputs up the top here, all the way, all of the I's are user inputs. So data A is going to be 64, there's hex 64, and data B is 19 in this case. LA and LB are asserted. So on the next active clock edge, after all of that's done, we see 0064 being loaded into the A register and 19 being loaded into the B register. So they're equivalent to decimal 125. S is asserted. When the next active clock edge comes along here at clock cycle 0, we see then us entering state 2. While that means EA is going to be set, EB is going to be set, and if the least significant bit of B is a 1, EP is also going to be set. Now, as it happens, B is 1, 9, so the least significant bit is a 1, which means that on the next active clock edge after we've entered state 2, we get A being added to P, which is 0, so we see A becoming 0064, right? And we see 19 becoming 0C, right? We're shifting that guy across. Then there's 2 cycles where it's zeros, so nothing happens here, nothing happens here. However, on the next clock cycle, so in this period here, we have 3 left down in the least significant bit positions of B. So 320, which is our 64 that's been shifted across now a number of times, 3 times I think, is going to be added on the next active clock cycle to 64. So we see that becoming 384, right? And of course we shift the 3, that becomes 1. So we're still left with a 1 there. We shift 320 across one more time, that becomes 640. So we've now shifted it 4 bits across to the left. And since we still have a 1 in the least significant bit position of B, 640 gets added to 384, so we see 09C4 in our final product. A gets shifted again, but it's of no consequence because B has become 0, and since B has become 0, on the next rising clock edge we enter state 3 with 09C4 in P. And you can do the calculations for yourself, that's 2500. So it did the right thing, it multiplied 100 by 25, yeah, which is pretty impressive. So are there any questions? And it did so really quickly in 6 clock cycles when it might have taken up to 8. Any questions? I know that's a lot to take in, so it's worth reflecting on what we've discussed and checking that you understand how these more and merely signals are being asserted within ASM and what that really means. In which clock cycle does that mean you're actually going to get an action occurring? All right? That's about the only tricky bit. All right. If there are no questions, we'll have a 5-minute break and then we'll do the Q&A bit. Pardon me. So no questions about the simulations, the code, the concepts? All right, I don't know that we're going to get any more people coming, so I was just going to go over the quiz problems that I thought were probably on average not handled as well as the rest of the questions. Look, I think on the whole, the quiz was done reasonably well. It might not seem so, but even a score of 7, I think, is quite okay in this quiz. Especially if you didn't study too much for it. Pardon me. Right. The question number here doesn't really refer to any particular question that you might have seen in the quiz, because this is the number that it has within my database of questions, as opposed to what it was within the quiz paper. So half the class would have got this question 18, and the other half would have got question 28. And look, I'd say maybe 50% of students got the right answer, and the other 50 didn't. So it suggests it's a little bit trickier. Pardon me. So the idea here with that question 18 is that you've got a T-type flip-flop. And you want to, and you've got some logic that you want to drive it with J and K to make the whole thing look like a JK flip-flop. Right? So how do we solve this problem? We know what J and K are, and we know what Q is, and we know what Q bar should be based on, or Q dash, QT plus 1, based on what J and K should be, or what J and K are. So we have to drive T to affect Q. That's the only input we have to change Q. So just considering the possibilities that we have, what do we want QT plus 1 to be, given the current JK setting and what we've got in Q? Well, it doesn't really matter what's in Q at this point in time. But if J and K are both 0, what should QT plus 1 be? It should be the same as what Q is, right? So it should be 0 and 1 in this case. So we do need Q. What if J is 0 and K is 1? Well, then K stands for clear. We want the next state to be 0 in both of those rows, right? And if J is 1 and K is 0, then that's the set condition. So irrespective of what the current state is, we want QT plus 1 to be 1. Pardon me. And if J and K are both 1, what should that do to the output? Toggle it. Right, so if we've currently got 0, it should become 1, and if we've currently got 1, it should become 0. All right. So if this were a T flip-flop, right, then we have to drive the T input so that we get the desired QT plus 1 output, right? So that effectively means that if we've currently got 0 and we next want 0, T should be 0, right? If we've got 1 currently and it should become 1, T should be 0. 0 to 0, 0, 1 to 0, well that means we've got to toggle. 0 to 1 means we've got to toggle. 1 to 1 means stay the same. 0 to 1 means toggle, 1 to 0 means toggle. Agreed? So, effectively, if we have this current state, this is how we've got to drive t. So the rows where t is asserted are these two and these two. So what's the expression that relates t equals? Well, we have in the first row and the last row both k and q, right? So, and it seems to be immaterial. It doesn't really matter what j is. So kq, or, so that covers the first and the last row. And these two rows, well, they have in common that j is 1 and q is not q, right? Or q is 0. So j not q. Right? So that's the logic that you have to, or the reasoning behind how you can figure out that B is the right answer in this particular case. Right. The next question is a little bit more straightforward, although it's not really super different. Rather than it being a D flip-flop, we have a T flip-flop, we have a D flip-flop. Right? So how should that be filled in? Well, when j and k are both 0, what are we doing? We preserve the current state. So it should be 0 and 1. Oh. Well, actually, I should just take whatever's the qt plus 1 column here, right? So it should just be 0, 0, 1, 1, 1, 0. Okay? And so the rows of interest are slightly different. We have this row that's of interest, and we have these three down here. Right? So what's the expression for D? Well, let's take this one and this one, because they eliminate J. So it's not K and Q, right? So that's those two rows. And then I have to do these two rows, which both have J and not Q. Is that one of the options? Yes. C, I guess. No, that's not the option. It has to be, is it B again? J not Q and not KQ. Yeah, it's B. B was a very popular answer. There was one person, I think, that literally randomly answered questions, and unfortunately they didn't stick to the plan of just always nominate the same letter if you're going to do that. So I think they got 2 out of 15. Right. Any questions on either of those? Okay, good. Did you have trouble with those? Any of those? Right. Now, this was a question that everybody got. and you had to determine what this code does. And I think it was, yeah, probably less than 50% got it right. What does it do? What's the key to unlocking what it does? So, which of the following statements best describes the action of the circuit when the input load is set to 0 and a positive clock edge occurs? So we're doing the else part, right? And a positive on a positive clock edge, right? So it's saying put 0 into Q0, and Q is listed as n minus 1 down to 0. So it's a normal sort of numeric value, most significant bits over on the left-hand side, least significant bits on the right-hand side. Put a 0 into the 0th bit, and for all the other bits, shift them over by 1 bit to the left, right, towards the most significant bit end. So what is that? What's the effect, numerically, what's the effect of that?
Doubles.
Yeah, it doubles. It's effectively just doubling the number because you're effectively shifting it over to the left by 1 bit position. I think many people, at least 30%, probably thought of this as being sequential and said that it clears the word. So no, a process is a concurrent, it's just a complex concurrent signal assignment statement. Everything happens in 1 clock cycle when the clock edge happens, right? It's just a descriptive way of describing complex behavior. So when it's not easy to describe that using just simple concurrent signal assignment statements. So the for loop in here, it's really just shorthand for saying Q1 is assigned Q0, Q2 is assigned Q1, Q3 is assigned Q2, all the way up to Qn minus 1 is assigned Qn minus 2, right? And all of those assignments all happen in parallel, so each flip-flop is just reading what its less significant neighbour is currently storing and doing that all on the 1 clock edge. So there's no sequential behaviour here. We know that because effectively none of the assignments that are created there are committed until you get to the very end, and then all of them are committed in one go. Or at least semantically, that's what is happening. Okay, you've had your hand up for a while.
That's right. I just want to confirm that the multiplying by 2 doesn't hold for all the values, right?
No. No, it doesn't. It doesn't in a computer either.
Yeah.
If you were to write for integer x, x times 2, the answer is not always twice x, right? Because you can have an overflow. It can become negative very quickly normally in a computer. Here it'll depend on whether it's been declared as being unsigned or signed. Well, here it's not even a numerical operation, but depending upon whether the word is thought of as being signed or unsigned, you could be overflowing. Okay, apart from that, none of the other explanations here work. It doesn't shift the word to the right. We've discussed this one, and it certainly doesn't rotate the bits of the word either. I don't think many people answered that one. Okay? Did this trip any of you up? Well, so far you've all been perfect respondents. You all got 100%. Very, very good to hear. Okay, now, here's one that even tripped me up the other day because I was asked to justify it and I wasn't able to at the time, but now I've thought about it again, referred to my notes, and now I know what the argumentation is. So, I don't know what fraction got this wrong. It would have probably been more than 50%. So we're given this parallel load shift register, and we're given certain timing characteristics here. I think they were the same ones that we've used in lectures with a TSU, a setup time of 0.6, TCQ of 0.8 to 1 nanosecond, hold time of 0.4, and a propagation delay for a k-bit gate of 1.01 times k nanoseconds. So the question is, what's the maximum clock frequency that the design can be clocked at? So the critical fact that you need in order to determine the maximum clock frequency is what the critical path length of the design is. And the definition of critical path length is it's the maximum delay between any two flip-flops. Right, so that means we're concerned with the delay between this flip-flop here and this flip-flop here, or between this flip-flop and that one, or between this one and that one, not between anything else. Okay? And what we have is a TCQ max of 1 nanosecond. We have two gates that we have to go through, two input gates, so 2.4 there, and we have a setup time of 0.6 of a nanosecond. So altogether that's 4 nanoseconds when you add those numbers together. And you know, you didn't need a calculator to then figure that that's the 250 megahertz answer that we're looking for. So the delay of this inverter here is not relevant because it doesn't contribute to a critical path in the design. Okay? Even though wires that are used in the design depend upon this inverter, that inverter is outside the design. It's part of the asynchronous part of the design before we get to the first flip-flop. And so we can change that at any time, and normally it's kept stable, so there's no sort of changing in it. The only things that are changing are the contents of the flip-flops. All right. Are there any other questions related to this? Okay. The next question was similarly tricky, although probably not quite as complicated, or maybe it's even more complicated, I'm not sure. Yeah, I think I was asked this one the other day and I couldn't immediately explain how it worked either. So we've got slightly different parameters here, and what we want to know is when can we change T and not impinge on the hold time that we have for the design. All right, so let me do this slightly differently. So let's assume we have our clock signal coming along like that, and we know that there's some period after the clock edge, TH, during which we do not want to change the D input. right? Because if we change the D input during that period of time, then it's possible that the output won't be latched properly. We could enter a metastable behavior, etc. So what the question asks is, you know, there's some period of time where if we change it prior to that instant, we're going to be impinging on this period of time because there's all of the latency of this network of gates here that we have to take into account. So only when we go past that period can we be sure that the change is not going to impinge on our hold time, right? Okay, so when is this instant in time is the question. When is it, how much before the active clock edge is it, is the way the question is framed. And in this particular case, you have two input gates again. Now the question is, do we need to include the inverter or not? So the two input gates, they're going to both contribute 0.02 nanoseconds based on the timing requirement here, the TPD. 0.01 plus 0.05 times 2 is 0.01 as well. So that's going to be 0.02. So the OR gate's 0.02, the AND gate's 0.02. Now, if we included the inverter, that would give us more headroom and push this time further. It gives us more headroom. So the latency is actually increased by the inverter and pushes us further out here. So we don't really need to include that inverter here. So we have a total latency of 0.04, and we know that this hold time was 0.03. So this latency here is 0.04. So this has just got to be, I know I haven't drawn it very accurately, 0.01 nanoseconds before the rising clock edge. I hope that's a convincing argument. Have I convinced you all? So the idea is, if I were to, so I've just said that it's 0.01 nanoseconds, right? Let's say we change it at 0.01, 0.01 minus delta, no, it has to be plus delta, before the rising clock edge, right? So if the rising clock edge is 0, and I change it now 0.01 plus delta, so a little bit further past over here, delta amount of time over here. Then that means that impact is going to be felt delta time before the end of the hold time. That's the minimum amount of time that it takes a signal to get through here, because if I take this lower path, it'll go through this AND gate, it'll go through that OR gate, 0.04 nanoseconds later, it's going to have reached, it's going to have reached that D input, but we'll still be in the hold time at that time. And so that's no good. But if we wait any delta amount of time after this 0.01, that pushes us beyond the hold time, and therefore we're not going to be affecting the value that's stored there. Are we satisfying setup time if we do it there? What's the setup time here? 0.06. Yeah, that's okay. 0.06. Yes, Because so if I were to change it at 0.01 nanoseconds before the edge, the value that I used to have is still going to be on D when the clock edge comes along. It doesn't get changed until after. And so setup time is still satisfied by doing that. Okay? Is that clear? All right. Are there any questions?
I sort of don't get how you got the 0.1 nanoseconds from taking the hold time from the total latency of the gates. I don't understand.
Okay. So what we care about is when does the signal at D change? Okay, so we want to know, and we know that we have to keep the signal at D constant for 0.03 nanoseconds after the clock edge. Any change that we make to T is going to take 0.04 nanoseconds at least to impact on D.
So 0.01 nanoseconds that time.
0.01 nanosecond gives me, together with the 0.03 nanoseconds after for the hold time, means I'm beyond the hold time when that change in D is going to actually occur. Is that right? All right. Anybody else? Any question? Okay. So some of you will have had this question, others will have had this question. In order to satisfy setup time at the input to the D flip-flops, at which time prior to the rising clock edge should the input T become stable? So this is using the same assumptions. So the setup time is 0.06 nanoseconds. Right. So now we have to include the inverter because while the minimum latency through this network is 0.04 nanoseconds, the maximum latency is 0.05 or 0.055 nanoseconds, given it's the TPD is 0.01 for the inverter is 0.015. Yeah? So the minimum time is 0.04, but the maximum time is 0.055. We've got to add that to the 0.06. So that gives us 0.115 nanoseconds prior to the edge. Is that clear? So if I don't take that inverter into account and only say it's 0.1 it would be 0.1 nanosecond prior to the rising clock edge, then I'll have satisfied it for the lower path, but then this guy's going to come through 0.015 nanoseconds later, and therefore I won't be satisfying setup time anymore, all right? Because it'll be impinging on the setup time period. Okay, good. Are there any questions? It's tricky, this time stuff, but it's really just shifting your mind from one deadline to a different deadline. Okay, if there are no questions, I'm going to move on. Actually, this is the last question that I'm going to cover, which was this one. I don't know, not everybody had this question. I don't know how many people got it right and how many people got it wrong. I would say that it probably was around a 50-50 result on this one. Did any of you have this question? Do you know how you went? Right. How about you all have a bit of a think about what the right answer to this is? And we'll go through it. Right, so the question comes down to implementing this function using cofactors and using Shannon's theorem with one variable, and in this case you're told that you're using variable x. So we're writing this as x outside of, well, not yz, or y not z, or not x outside of y or y not z. Can you all see that? So it's just doing the Shannon's expansion on those terms. Since this term doesn't involve x or not x, it involves both and has to be included in both, right? Okay, so in terms of this diagram, we have this lookup table here. 1 has got to implement the cofactor of f with respect to x bar, which is this guy here, right? So this can actually be simplified, can't it? What can this simplify to? Just y. Good. So what would the lookup table look like? The WXYZ lookup table for this guy if we were implementing the cofactor of f with respect to x bar. So y is the upper input, so it's in 1. So when it's 0, we want f to be 0. And when it's 1, we want f to be 1, right? So it'd just be 0, 0, 1, 1. 2LUT3 is going to be implementing the cofactor of f with respect to x, which is the exclusive OR of y and z. So what's its bit stream going to be?
0, 1, 1, 0.
Great. 0, 1, 1, 0. Okay? That's this guy. Now, what's this 2LUT2 going to be implementing? The AND of not x and the cofactor of f with respect to x, right? So when this guy is 0, we want to output a 0 when x bar is 0. And when x bar is 1, we want to output what? So when x is 0 and f of x bar is 0, we want it to be 0, right? And when it's 0 and 1, we want it to be 1. When x bar is 1 and f is 0, well, actually, it doesn't really matter for these guys what W and X is. But when X bar, sorry, it does matter when X is 0. Sorry, when X is 0, we want 0 and 1 to be here. When X is 1, it doesn't really matter because what this is meant to be implementing is the AND of not X and F of X bar. So it doesn't really matter what these values are when N is 1, can be 0. What's important is that you have a 0 and a 1 there. As for the bottom one, what does it need to be? It's the AND of X and F of X, right? So when F of X is 0 and X is 0, does it matter what the output is? Yes, it should be 0, right? Only when X is 1 and this guy is 1 should the output be 1. In every other case, it should be 0. So it's the AND function that it's implementing, right? So it should be 0, 0, 0, 1. What's this guy implementing? The OR of those two input LUTs, LUT2 and LUT4, right? So it should be 0, 1, 1, 1. That's what it's implementing. It's just the OR of these two things. Okay, so now we're in a position to examine this, and it says here that which one's false, I think, is what it asks. Which of the following statements is false when implementing this particular function? So the configuration of 2LUT3 has the bit pattern 0, 1, 1, 0, 2LUT3. Well, that's not false. We determined that that's what it should be. The configuration of 2LUT4 has the bit pattern 0, 0, 1, 0. Well, that is false. We determined it was going to be 0, 0, 0, 1, right? The configuration of 2LUT5 has the bit pattern 0, 1, 1, 1. That's correct because we determined it was going to implement the OR gate, and the arrangement can be simplified by removing 2LUT1. Well, that's also correct because we could just put Y directly into 2LUT2, right? Because that's what we determined over here was all we needed. We don't need Z. So the answer is B, okay? But yeah, there's a bit of work to figure it out. Was it an unfair question? All right. Okay. Are there any other questions as far as the quiz is concerned? Right. Let's forget about that then. Oh, so we have 5 minutes effectively. I've got to go. Are there any questions on the exercises? Have you had a chance to have a look at them? It's very large, isn't it? Oh, that's too small. Exercises. How come that's gone off? Right, so I'm talking about the week 7 exercises which we missed because of Good Friday last week, and this week's exercises on FSM on FSMs as well. So if you haven't had a chance to look at them, look at those exercises, and then if you've got questions about them, come to me next. We'll talk about them next week because there's still 2 more weeks to go. We can do a Q&A in week 10 too, if need be. All right, yeah.
Is week 10 just going to be like a revision week, or?
Week 10?
Yeah, because I mean, from memory,
Usually I don't have a lot to say in week 10 other than to go over where we've been and what the exam's going to be about. Now, I've made no preparation so far for the exam, so I can't tell you anything about what the exam's going to have in it. But there are the sample papers, the previous sample papers. They're actual papers that were previously given. So they're the best sort of source. It'll be similar form. Won't necessarily be the same question though. Look, I think while you're still working towards finishing off the labs, that should be your main focus for the time being. Getting as much experience at thinking about the problems that you're trying to solve, and solving them is, solving them within the confines, the timeframes of the labs, I think is really useful. And discussing any questions that you've got with the demonstrators is probably the best approach at this point in time. But yeah, I would not imagine, although I'm running a little late because I didn't really expect Easter. So I'm not going to finish this lecture until at least Tuesday next week, which means that I might make a start on the technology still next week. But that's just a sort of a one to 1.5 hour lecture. It doesn't take too long. So I think, yeah, there isn't going to be substantial new stuff, if anything, in week 10. Okay. Any other questions? All right, good. Have a good weekend. Good luck with the labs. Hopefully you're finishing off lab 5. If not, started on the lab 6. If you haven't yet used the labs, please do. Just get familiar with the lab environment, because that's what you're using in the exam. You can't use your own laptop then. All right? Thank you. See ya. All good?